Hi students, in the previous videos and all, you have been doing this Thevenin's theorem and Norton's theorem using only independent sources, right? So now we are going to learn to do these same problems, the same theorems using dependent sources, okay? So like I already told you, the difference between this is that here to find the value of the Thevenin's impedance and Norton's impedance, you need to find both the Thevenin's voltage as well as Norton's current. Because the equation that you have used to, if there is a dependent source anywhere in the circuit, then the equation you need to use to find the Thevenin's impedance or Norton's impedance is VTH by IN. That's the only equation you can use. Okay, that is the difference between this problem and the previous problem. The rest of it is the same. Okay, you are going to deal with this dependent source like a normal source, in which you just need to define the controlling factor. Here the controlling factor is I, so you just need to write the equation for I. Just like everything is same, the mesh analysis is, we are basically applying mesh analysis in the circuit. The only difference comes in finding the Thevenin's impedance or Norton's impedance. Okay, so here one thing you need to understand is that if there is a dependent source over here, if there is a dependent source anywhere in the circuit, then whether they have asked for Thevenin's equivalent or Norton's equivalent, it does not matter, because you still need to find both VTH and IN. Because unless you can find VTH and IN only, then only you can find the Thevenin's impedance or Norton's impedance, because you are using the equation VTH by IN. So you need to find both the values in that case. Okay, so let's do this question. So finding the VTH is exactly the same. The difference comes in finding the impedance. Okay, so let's do this question. Obtain the Thevenin's equivalent across the terminal. So here you have a dependent source. Okay, so a dependent source, which means you need to find the equation for I. Okay, so what will be the equation for I? Well, if you look over here, this is plus and minus. This is what you call as VTH. Okay, this is VTH. This open end is called as VTH. So if this is open, which means I2 is equal to 0, right? Let me mark over here. This is I1. Okay, I'm not going to mark I2 over here because that will be so stupid. And I2 is equal to 0, right? I2 is equal to 0. Okay, I'll write that I2 is equal to 0, and now I'm going to write the equation for I. What is the equation for I? What is I? I is the current through this branch, or I is the current through this 4 ohm resistor. And what is the name of the current that goes through this 4 ohm resistor? It is I1. Or in other words, I is equal to I1. Okay, I is equal to I1. That's it. Now you're going to treat this as a normal source, and wherever you see the value I, you replace it with I1. That's all. So let's do this question. So first I'm going to apply here equation for I1. Okay, that is equation for mesh 1. Equation for mesh 1, right? So here you can see that this I1 into, and I1 is touching these two elements. It is 4 minus j. So 4 minus j, okay, minus I2 into minus 1j, okay, is equal to, now what about the voltage source? What about the voltage source? Here you can see that this is I1, this voltage source, this I1 is coming out of the positive terminal, right? Or means this positive terminal is generating I1. So it is plus 10. 10 angle 0 is 10. Okay, don't forget that. And what about this one? Over here, this I1 is going into the positive terminal, right? Into the positive terminal, which means this positive terminal is not generating current, it is opposing current. Therefore, it is minus 2I. This voltage source is minus 2I. Okay. So now, like I said, we already know that I is equal to I1. So I will substitute I1 over here. So which means I will express this equation in terms of I1 and I2. Of course, I2 is also 0. So you can remove this term also. So we are left only with I1. So therefore, it is like this, right? I1 into 4 minus j. I2 is equal to 0. So forget about it. I'm going to bring this thing over here. It will be plus 2I1, right, is equal to 10. There you have it. So in that case, I1 is equal to, let me see, what is I1? I1 is equal to 10 by 6 minus j, right? I1 is equal to 10 divided by 6 minus j. Let's see what's the value? 10 divided by 6 minus j, and the answer is 1.622 plus 0.27J, and its polar form is given by, just for assurance we're just putting it here, it is 1.644 angle 9.462 degree amperes. Okay, so this is the value of I1. Okay, so now I found the value of I1. Next I'm going to find the equation for VTH. Okay, so the equation for VTH or equation for mesh 2, but this is not a mesh, so that's why I'm not writing equation for mesh 2. This is equation for VTH. Okay, so here in equation for VTH, just like writing the equation for mesh 2, minus I1 into, and here it's, in this mesh 2 I1 is touching only this element, so it is minus J or minus 1J plus I2 into, it's touching these two elements, right? That is, this is 1J, no, this is 2J, sorry, this is 2J. Okay, this is 2J and this is minus 1J, so we have 2 minus 1 is 1J, alright, plus VTH. Why it is plus VTH is because this I2 current is flowing from a higher potential to a lower potential, right, which is what a current is supposed to do. So therefore that's why I'm representing it as plus VTH. This hypothetical current I2 is actually flowing from a higher potential to a lower potential, so that's why it's written as plus VTH. Is equal to, are there any voltage source over here? There's a voltage source over here, it's called as 2I. So, and this I2 is flowing out of the positive terminal, right? It's flowing out of the positive terminal, which means this positive terminal is generating I2, so it will become plus 2I. So this is equal to 2I. Okay, and this is basically I1 into J. I2 is 0 plus VTH is equal to 2I is equal to I1, so I'm going to write it as I1. In other words, VTH is equal to 2 minus J. So I1 into 2 minus J. This is the value of VTH. Or, and we already know what is I1, right? I1 is 1.622 plus 0.27 J into 2 minus J. This is the value of VTH, which means, let me see the answer. (1.622 plus 0.27 J), right? So this answer, right? This answer I will multiply it with 2 minus J, and I will get 3.514 minus 1.081 J. 3.514 minus 1.081 J. Okay, and that means VTH is also equal to the angle. I want to find the angle. The angle is option polar form, then you get is 3.676 angle minus 17.103 degrees volt. .6 minus 70, yeah, got it. So this is the voltage I got. Okay, this is the correct answer. So now I found the value of VTH. Next I am going to find the Norton's current. Okay, why I am going to find, so I know this is Thevenin's equivalent, but we have already found VTH. But like I said, if you want to find the Thevenin's impedance, since there is a dependent source, you are only able to use this equation, because it's a dependent source, right? Why are we using this equation? Why are we using this equation and not the other equation? You see, because the normal method of finding the Thevenin's impedance is that the Thevenin's impedance is the resistance across these two terminals when we are removing all the sources. That is, we remove the voltage source and we remove the current source. How do we remove the voltage source? By shorting the terminals. How do we remove the current source? We open the terminals, right? So if there's a voltage source, we will short it, and if there is a current source anywhere, we will open it. So that is how we find, and then we find the equivalent resistance. That is how we find the Thevenin's impedance or Norton's impedance. But here in this case, there is a dependent source. This is not an independent source, this is a dependent source. So if you see a dependent voltage source or dependent current source, you cannot short it and you cannot open it. You can do neither of those things. You can only do those things if those voltage sources and current sources are independent. If you see an independent voltage source, you can short it. If you see an independent current source, you can open it. But if you see a dependent voltage source or a dependent current source, you can neither open it nor you can close it. You can't do nothing about it. So which means then you have to go for plan B, which is using this equation. This is the second option of finding the Thevenin's impedance or Thevenin's resistance or whatever. That is, we find the Thevenin's voltage, we find the Norton's current, and we take the ratio of it. Okay. So now I'm going to find the Norton's current. So let's do the same question. That is, I'm going to find the IN, right? So I will draw the circuit again. To find IN, let me write that. To find IN, comma. To find IN, this is the voltage source. Okay. Resistor over here. You have a capacitor, and then you have a dependent source. Join it, and then we have a inductor over here. Okay, and this is 4 ohm. This is minus 2. This is minus J. Yeah, this is minus 1J. This is minus 1J. This is 2I. This is 10 angle 0. Okay, and what else do you have? The inductor is 2J. Okay, just 2J. All right. So now I'm, like I said, I'm going to find IN. So to find IN, what I do is I join these two terminals, and the current that is flowing from A to B. The current that is flowing from A to B is the Norton's current. Okay, IN. Right. So now I'm going to find the value of IN using mesh analysis, which means this is I1 and this is I2. So in that case, what is the name of the current through this branch? The name of the current through this branch is I2, right? And the same current is IN, which means the equation for IN is equal to I2, which means if you want to find the value of IN, simply find the value of I2. And what is here? There's 2I, right? And what is the equation for I? I is the current, of course, I is the current through this branch, right? So what is the equation for I? I is equal to I1, right? Because the same current, the current through this branch is also called as I1. So therefore, I is equal to I1. Now I'm going to apply mesh analysis. Equation for mesh 1. Equation for mesh 1 is I1 into, and we have 4 minus J, right? 4 minus J, that's the only two elements over here, right? Only 4, and there's minus J, plus, no, sorry, minus I2 into, and it's touching only this element, that is minus J, okay, is equal to, now what about the voltage sources? This I1 is, like I said, this is just the same like before, right? This is 10 minus 2I. This is plus 10 because this voltage source is generating I1. This is minus 2I because this voltage source is opposing I1. That's why you got this equation. So therefore, but 2I, I is equal to I1. Therefore, this is 10 minus 2I1. So which means I'm going to bring this thing over here. This will become I1 into 4 plus 2 is 6. So you have 6 minus J. Then here you have plus I2J is equal to 10. Okay, this is equation 1. Now I'm going to do equation for mesh 2. Equation for mesh 2. Equation for mesh 2 is this equation. Here I1 is minus I1. Sorry, it's minus I1, and here you have minus J plus I2 into, and I2 is touching these two elements, that is 2J minus J, which is J itself. And that's it, right? Those two, and that's it. This is equal to, and here this I2, this 2I is generated. The I2 is flowing out of the positive terminal of 2I, so it is plus 2I. So plus 2I, okay. And since this is 2I, I is equal to I1, so it is 2I1. So bring this 2I1 over here. You have, this is basically, let me write this equation. This is I1 into J plus I2 into J is equal to 2I1. In other words, I1 is equal to minus 2 plus J plus I2 into J is equal to 0. This is the equation for mesh 2. So therefore now I'm going to, what I'm going to do, should I, you see over here you have I2j, here you also have I2j, so no need to apply matrix form, right? I can simply subtract these two equations. Yes, I will simply subtract these two equations and then I can find it. It will be much more easier for me, right? So let's do that method. So here it is I1 into 6 minus j plus I2 into j is equal to 10, and then here you have I1 minus 2 plus j plus I2 into j is equal to 0. So now what you do is we are going to subtract these two equations. So if you're subtracting, then this will become minus, right? So minus of inside this will become plus, this will become minus, this will become minus, and this will also become minus. So we have basically what we have here is I1 into here 6 plus 2 is 8, and minus j is minus 2j. Okay, these two will cancel each other, and 10 minus 0 is 10. Okay, if you want you can apply matrix method, okay, but I find this method more simple, that's why I'm using this method. You don't have to follow it. 10 by 8 minus 2j. So I1 is equal to 10 by 8 minus 2j. If this is the equation for I1, then what is the equation for I2? I2 is, let me see, I2 into j is equal to 10 minus I1 into 6 minus j. Okay, right? And in that case, then 10 minus, what is I1? I1 is 10 by 8 minus 2j into 6 minus j. Okay, you see, I want to tell you something. This I1 is different from this I1. Okay, this I1 is different from this I1. This I1 is different from this I1 because this is the value of I1 when you are trying to find the Thevenin's voltage. There the circuit is different. Here the ends are open, the terminals are open, whereas in this case the value of I1 is different because this is, you are finding the I1 of another circuit, and in this circuit the two terminals are shorted. Okay, usually students make mistake, they use the same value of I1 in order to find the Norton current. That's wrong. You have to find the new value of I1. Okay, so new value of I1 and I2. So the value of I2 is, the value of I2 can be, now you can write the value of I2. To find the value of I2, what I will do is I will multiply this with j. If I multiply, no need to multiply, just simply follow the same method, much more easier for me. So what will I get over here? This is 10 into 6 minus j divided by 8 minus 2j. Yes, 10 into 6 minus j divided by 8 minus 2j is equal to, wow, this is equal to 10 minus 7.353 minus 0.588j. Okay, this is the equation, and so that means this is the answer. So what I do is I will take 10 minus 7.353. What is 10 minus 7.353 is equal to 2.647. So this is equal to 2.647 minus 0.588j. I2 into j. Okay, now I'm going to find, so what I will do is I will multiply this whole thing, or what I will do is I will just find the value of I2 is equal to, it is I2 is equal to 2.647 minus 2.647 minus 0.588j. Okay, 0.588j divided by j. Correct? We have minus 0.588 minus 2.647 J, and I2 is, that is I2, or I2 is also equal to, let me take its angle, option, polar form, 2.712 angle minus 102.524 degrees. Okay, this is the circuit. This is the value of I2, which means the value of IN, is equal to, the value of IN is equal to 2.712 angle minus 102.524 degrees. Okay, the answer is correct. Okay, I just checked it, so the answer is correct. So which means the value of ZTH is equal to VTH by IN, which is equal to, what is the value of VTH? Where is VTH? The value of VTH is, I'll take the complex form, 3.514 minus 1.081 J by, and here it is minus 0.588 minus 2.647 J, which is equal to this 3.514 minus 1.081 J. Okay, 3.514 minus 1.081 J divided by minus 0.588 minus 2.647 J. Okay, you will get the answer as 0.108 plus 1.352 J. Option, and its polar form is 1.356 angle 85.425 degree amperes. This is the, ohms, this is ohms. This is ZTH. Okay, 1.356 angle 85.425, which means your circuit is like this. Okay, okay, the value of VTH is equal to 3.514, or we express the polar form, 3.676 angle minus 17.103 degree volt, and the value of ZTH is equal to 1.356 angle 85.425 degree ohms. Okay, this is the value of ZTH. Okay, this is Thevenin's equivalent, and the Norton's equivalent is like this. Norton's equivalent, ZTH is equal to 1.356 angle 85.425 degree ohms ZTH, and the current source is IN is equal to, Norton's current is, value for Norton current you got is 2.712 angle minus 102.524 degree amperes. This is the value of IN. Okay, this is the value of VTH, this is the value of I. This is basically source transformation, right? Source transformation is that if a voltage source with a series impedance is equivalent to a current source with an parallel impedance. This is what you see. This is basically source transformation actually. That's how we got these two theorems. And here you can see that here the question was to find Thevenin's equivalent. So no need to draw this circuit, okay? But I just want to make you understand that if there's a dependent source, then anyway you have to find both VTH and ITH. Sorry, both VTH and IN, the Norton's current, right? So in that case, it doesn't matter whether it it is Thevenin's or Norton's, because you have to find both the values in order to find the value of ZTH. Okay. Like I said, this is applicable. This is only applicable if you can use this method if you have any single dependent source anywhere in the circuit. Okay.